So, welcome everyone. Very happy to welcome Professor Bilas Pachori here from IIT Indore. He was supposed to be here a long time ago. I think we applied for your visit 2 years ago or 3 years ago, but then the pandemic happened and then actually the application wasn't valid anymore and we had to reapply. But now we're very happy that maybe we have the fourth time window before the next wave hits so that we can have him here. Just a few words about Ram. He's from IIT Indore, which are renowned institutes in India. You can think a bit about them like MPIs here in Germany. And he's here 2 months on a DAD bilateral exchange of academics program. So he comes here, and I hope if the pandemic allows that I go back to him. Just a few information about his bio. So he made his Bachelor of Engineering in Electronics and Communication Engineering from Rajiv Gandhi Technologies University in Bhopal, India in 2001, and an MTech from the Institute of Technology, IIT, in Kanpur, India in 2003 and 2008 respectively. He then went to Europe for a short time, was a postdoctoral fellow at the Charles Delaunay Institute in Troyes in France, and I directly after this became assistant professor at Communication Research Center at the International Institute of Information Technology in Hyderabad in India, 2008 and 2009, which was his last station before he then moved on to the IIT in Indore, where he is now and since 2009, and going through the different stages of the career since 2017 is full professor. He has research interests in many areas, including signal and image processing, medical signal processing, so things that we care about a lot, non-stationary signal processing and speech signal processing, among others. He is a very widely cited and influential researcher. Just check out his Google Scholar profile, which is very, very impressive. And if you wish, I'm not going to waste any more time on all the prizes he has won. And I don't know how many editorships he has on many different things and many things that he does as well. So not to delay anymore. Very happy you're here and looking forward to your talk.
Yeah, thank you very much, Professor Adik, for nice introduction. And I would like to convey my thanks to Professor Adik for providing me this opportunity to be part of your team and also provide opportunity for deliver this talk. Thank you very much. Let me start today's talk. It is on multivariate signal processing for EEG analysis and classification. So in this talk, actually, we will see the use of the multivariate signal processing. So conventional way, when we process signals, we actually consider channel-wise. So like in real life, many scenarios are there where we encounter multiple signals at a time. So the conventional techniques, they actually process signals channel-wise. So that in this talk, we will see when you process these signals jointly, then there are certain advantages that also will be highlighted in this talk. And we have developed some signal processing techniques towards application to EEG signal analysis and classification based on these multivariate signal processing that also will be presented. And we will also see these conventional methods for signal analysis, which are based on time domain and frequency domain. They are not adequate for non-stationary signal analysis. So we will see in this talk when you combine both of them, time and frequency domain. So time frequency domain analysis of multivariate signals, when you consider this multi-channel EEG signals together, in that scenario, we have proposed multivariate time frequency representation that also will be explained. So with this background, let us start this talk. So this is the overview of this talk. First, we will see introduction. And after that, motivation will be provided why this multi-channel signal processing is required. And then we will see empirical mode decomposition actually briefly. And also, what is the motivation for use of empirical mode decomposition? That also will be explained. And we will highlight its limitations and that actually motivated to develop recently signal processing techniques, which are like empirical wavelet transform, iterative filtering. And then we have extended them for multivariate scenario or multivariate cases that we call empirical wavelet transform, and this is multivariate empirical wavelet transform, and its application for detection of epileptic seizures from EEG signals will be highlighted. And then for the iterative filtering, we have extended it into multivariate iterative filtering that will be explained, and its application for detection of schizophrenia using EEG signals will be explained, and in the end, conclusion will be provided. So actually, what is the need of signal analysis? That is very important application of signal processing. And in real life, we encounter with many signals. For example, electroencephalogram, EEG signal, electrocardiogram signals, ECG signals, and they are the output of the, for example, EEG. It is the output of the brain. And we perform analysis of EEG signals to understand the state of the brain. And these signals are highly unknown. So how to perform analysis and how to extract the information. So this idea actually was proposed 1807 by the Fourier, Joseph Fourier, and he represented these complicated signals. They are highly unknown signals to us in terms of sinusoidal functions or simple functions. So these complicated signals which are unknown to us, they are represented in terms of simple signals or non-signals. So in that way, this complicated problem or complicated signal is represented in terms of non-signals. So we can understand that. So this Fourier transform, what we do actually, we represent signals in terms of sinusoidal functions. So you can see one example, right hand side in the slide. There are two kinds of signals. One is stationary and second one is non-stationary signals. So non-stationary signals, actually we use mathematical models to represent the signal. If any of the parameters is changing with respect to time, then we call them non-stationary signal. And here you can see its frequency changing with time. So this first signal is stationary signal and second signal is non-stationary signal. So because it's frequency changing time, but when you apply Fourier transform, then you can see in both cases you are getting same Fourier spectrum. So that is actually one of the serious limitation of the Fourier transform when you are considering classification of the signals based on the stationarity and non-stationarity. So because when you perform this Fourier transformation, then entire time is integrated. So there is no time information in the frequency domain. So when you are in frequency domain, there is no time information, and when you are in time domain, there is no frequency information. Both are disjoint. So due to this reason, this Fourier-based representation actually is misleading, because the same spectrum can be corresponding to a stationary signal and it also can be corresponding to non-stationary signal. So due to this limitation, there has been two directions in the literature to come up with such kind of basis functions or non-functions which can represent non-stationary signal in unique manner. You can do nice analysis of non-stationary signals. So such kind of actually basis functions, they are amplitude and frequency modulated basis functions. So we allow this varying the sinusoidal parameters. So sinusoidal parameters like amplitude, frequency, and phase. And if you are able to come up with the time varying parameters of such models, then such kind of actually models will be highly suitable for non-stationary signals. So this has been the motivation in the literature, and on that basis, there have been two directions in the literature. One is where actually we design basis functions from our side. So like man-made basis functions like sinusoidal functions, wavelet transforms, we design wavelet from our side and we represent real-life signals in terms of these functions. But these functions like, for example, EEG signal. EEG signal is not sinusoidal function. EEG signal is not wavelet, but we are representing this EEG signal in terms of sinusoidal function, in terms of wavelets. So this is fixed basis functions, and where actually we design basis function from our side, and in that way this is the one direction. Other direction actually that has got a lot of attention these days, that is adaptive signal decomposition. So now you don't need to design basis functions from your side. These basis functions will be extracted from the signal itself. So we develop iterative approaches, data dependent methods, where these basis functions, whatever we get by using this data dependent approaches, they are part of the signals. So we call them intrinsic mode functions because they are part of the signals. And based on these approaches, so adaptive basis decomposition, there are various methods actually have been proposed in the literature, which includes empirical mode decomposition, empirical wavelet transform, variation mode decomposition, etc. So in all these methods, the main aim of the decomposition is to obtain the amplitude and frequency modulated sinusoidal functions or AM/FM kind of models for the analysis. So here you can see this is this model that ut equals to at e to power j phi t, the simple time varying sinusoid. We also call it amplitude and frequency modulated. So this is more general form of the Fourier basis functions, where we use sinusoidal functions, parameters were constant, but here we are allowing them to change with time. So this is suitable for narrowband real life signals. Then with the help of such narrowband signals, we can represent this multi-component signal xt in terms of these narrowband AM/FM signals. So this is multi-component AM/FM model, and this multi-component AM/FM model can be generalized for multivariate case. So left-hand side you see this multivariate extension of narrowband signals, AM/FM signal, and right-hand side you see multivariate form of the multi-component AM/FM signal model. So this is in fact in a real life whatever we signals encounter, this multivariate multi-component signal model is perfectly suitable for that. So this is actually the signal processing side. Now what is the motivation for this multivariate signal processing? So in real life actually we have many scenarios where at a time we record many signals. For example, like vibration signal analysis, when you study the gear fault diagnosis. So at a time you have many vibration signals. And second scenario, like EEG signal recording. So when you put this multiple electrodes in the form of cap, then at a time you record many signals. And third scenario, you see the ECG signals, electrocardiogram signals, which measures the electric activity of the heart. And at a time you can get many signals, ECG signals. So now in all these scenarios, what actually literature people do, they process these signals channel wise. So in that way actually we are ignoring the mutual information or this correlation that is existing among each other, these channels. So that is actually one of the problems. So due to these reasons, this new area of signal processing that is known as time frequency analysis of multivariate signals, where we will not do channel wise processing. Instead of that, we will consider all signals together. So that actually that is known as multivariate time frequency analysis that we will see in this talk. And this is actually happened due to lot of the development in the sensing technologies. These days we have very good sensors. At a time you can get lot of signals. At a time, in the old time there was only such sensors were not available. So univariate signal processing was highly suitable. But due to development in the technology, now it is easy to record multiple signals, and with the help of multivariate signal processing, we can analyze them perfectly. And also, this one of the actually problem, this adaptive signal processing, this is highly suitable for signal processing, but is data adaptive or data dependent nature. It gives you different components for different signals. For example, for one EEG signal, you can have 5 components, 5 basis functions, intrinsic mode functions. For other signal, you can have 10. So this because this is data dependent approaches. So due to that, actually, this multivariate signal processing plays an important role where mode alignment property can be preserved. So when you do this multivariate signal processing, then each signal of this multi-channel data will have same number of components. So that is also one of the actually important motivation for this multivariate signal processing. So that we will see in this talk in detailed manner. So this empirical mode decomposition that was actually proposed by Huang and others in 1998, which works in different way for signal processing. Like in case of Fourier transform, we design basis function from our side. In wavelet transform, we design mother wavelets from our side. But here actually you don't need to design anything from your side. This method is data dependent. You just give data, it will decompose into components. So that is data dependent method. And what is the motivation for this EMT method? Let us briefly, I will explain you. So like in case of Fourier transform, we use sinusoidal functions. So they are periodic in nature. They extend from minus infinite to plus infinite. So due to this infinite spread of these basis functions, resolution that is actually proportional to 1 over the spread of the signal. So these sinusoidal functions, they have infinite spread. So due to that, their time localization is 0. or time resolution is 0. So these sinusoidal functions, they are not able to represent non-stationary signals in efficient manner, because non-stationary signals, these properties are changing with time. But sinusoidal functions, they are not suitable for non-stationary signal representation because their properties are not changing with time. So in order to have these sinusoidal functions suitable for non-stationary signal processing, in the literature, the short time Fourier transform was proposed, STFT. That is also known as windowed Fourier transform. So what we do actually, we divide this non-stationary signal into different segments. Then we apply Fourier transform to each segment, and we assume that within each segment signal is stationary. Then arrangement of this Fourier transform gives us short time Fourier transform, STFT. And here also, once window is fixed, then you don't have any flexibility to change the window size. And there is no thumb rule which will suggest us what should be the size of the window and what should be the type of the window. So this actually, this is a serious limitation of STFT. And sometimes when we have different frequency components present in the signal, they require different sizes of the window. For example, if you have low frequency component, then analysis window should be wide enough. When you have high frequency components, then analysis window should be narrow enough. So that flexibility is not there in the this STFT, short time Fourier transform. So that actually motivated use of the wavelet transform. In wavelet, actually what we do, we see the signal at scale. So for example, if you want to have good time resolution, then see signal at low scale. If you want to have poor frequency resolution, then see at large scale. So in this poor time resolution, then you see at large scale. So in the different scales gives you different kind of resolution. So low is if you want to resolve low frequency component better way, then go for the large scale. And if you want to resolve high frequency component that are well localized in time domain, then you go for low scale. So scale actually is very important parameter, and that is the whole part of this actually these concepts. So I will give you one example. If you see the legs of the elephant looks like a tree. If you see the tail of the elephant looks like a snake. But elephant is not a tree, elephant is not a snake. Elephant will be looking like elephant when you see a proper scale. So scale is very important part. And actually in literature now people are looking instead of time and frequency parameters, now they have started looking the signal at various scales. And that is what the purpose of wavelet transform. In wavelet transform, good thing is that it can be represented with the help of filter banks. We have nice two filters, low pass filter, high pass filter, and the low pass filter version will give you approximation, and high pass filter will give you details. And you can implement it with the help of filters. And there is no thumb rule which will suggest us how to select number of labels in the wavelet transform, and which mother wavelet should be used for the signal decomposition. So this motivated to develop signal analysis technique which are based on the data adaptive nature, based on the selection of the basis functions, free selection. There is no need of the design of the basis functions. So that was the motivation for empirical mode decomposition. Empirical mode decomposition, there is no need of the design of basis functions. You don't need to select anything from your side. You don't need to design anything. No a priori information required. You just take the data, it will decompose it. So this is the one example of this empirical mode decomposition, and which is highly suitable for nonlinear non-stationary signals. So here you can see this is the signal. Then actually in this EMD method, we have to determine maximas and minimas. So first step, you determine maximas of this signal, then minimas, then you interpolate both of them. So you will get two envelopes. One envelope is corresponding to maximas, other one is corresponding to minimas. Then both envelopes we average both of them. That gives you instantaneous average mean, and this instantaneous mean that we subtract from the signal. So this we call residual, and residual should satisfy two conditions. One condition say that this number of extremas should be equal to the number of zero crossings or differ at most by 1. So this condition ensures that whatever IMF you are getting, it is like sine cosine function. And second condition says at any point of time, this average value of these two envelopes is 0. So this condition ensures that whatever is IMF you are getting, it is like symmetric in nature. So by satisfying these two conditions, we actually, the whatever intensive mode functions you obtain using this method, EMD method, that is narrowband in nature, symmetric in nature, and it is amplitude and frequency modulated sinusoids. So here you can see, and this actually, this is iterative approach. So what we do, we obtain first IMF using this, satisfying this condition, and after that, for second intensive mode functions or IMF, we subtract this first IMF from the signal, then we determine the residual, and then we repeat the same process. So then we obtain the second IMF, and our third step, we the first two IMF we subtract from the signal, then we determine third IMF. So in that way, we continue till all IMFs are obtained. So in the end, we obtain the residual. From that, no IMFs can be derived. So,
short question. So, what are local extrema? How do you determine the locality? Because it seems again that you need a free parameter about the location, right? Or is there only one local or two local extrema in the very beginning? So basically, how do you define a local extreme?
yeah, it is here actually. It is for entire scale. Like for this is global, like 100 samples. So we determine that this is global maximas.
Okay.
And global for this entire scale, like 100 samples for entire. This is the local minima, but at any point of time, this has local characteristics.
Okay.
Design, but it defined based on the like any length of the data.
Okay.
So.
Sorry for interrupting. So then the first component you would get, it's the one on the top right, right? The first component is the one on the top right. It's like this.
Yeah, that first one, this one.
The first, it's this one.
This one, the first component.
Oh, okay.
This first component since it is based on the maximum minima. So that will be the like highest frequency component. It will have more number of maximum minimas. So it is the lowest. This is the lowest scale present in the data, or highest frequency component of the data.
Okay, so the lowest minimum maxima is basically this point of the one before. So local maximum is the point before it is lower than this, and the point following it is lower than this.
Yeah.
Okay, and this is why it's high frequency. And if you take this out, you go into.
So we are assuming that this all frequency components, they are arranged with different actually amplitudes. So one by one we are removing all of them. So the higher that will be the which has highest number of maximum extremas will be removed. Then others number will come. So like one by one we remove all of them. So here in this. The first IMF, which is corresponding to the highest frequency, and the last IMF, for example, in this case, 8th IMF, that is corresponding to the largest scale of the data. So that is to the approximation, like that. And in the end, actually, this you get the residual. So that is also, it has been used in the literature like baseline wander removal. So because this is like time varying DC, it gives you automatic manner. There's all fluctuations from the data will be removed in terms of IMFs. In the end, you will have nice time varying direct component DC, time varying DC. So it is like your baseline wander that also can be estimated this empirical mode decomposition method. So based on this approach, various multivariate versions of EMD have been developed, which includes complex empirical mode decomposition, rotation invariant complex empirical mode decomposition, bivariate EMD, and multivariate empirical mode decomposition, fast multivariate empirical mode decomposition. So here actually, yeah.
What are the relationships between those components? For example, in PCA, all components are orthogonal to each other.
Yeah, that is actually here. This decomposition is suitable for nonlinear signals and non-state signals. So orthogonality here, is not very significant. It doesn't make physical interpretation. Like orthogonality is well justified when you like functions, so like sinusoidal functions, maybe they are orthogonal. Here actually they are not orthogonal, but they are near to orthogonal. because they are they can have different frequency components that overlap to each other. And this Flandrin and others, Patrick Flandrin group actually from France, he has shown that actually this EMD method, it is one kind of wavelet decomposition. Here you don't need to design wavelets, don't need to select a number of labels, but whatever this signal components you have, it is like multi-resolution analysis that we obtain using wavelet transform. So you have component different scales. So they may not be orthogonal.
Then I have another question. So how is it robust to noise? For example, you have
that is what this is a good question. So this method actually is not robust to noise because it is based on the time domain, and this noise is sensitive to the time domain. So it will affect your envelope, maxima, minima, and if your signal has any little bit noise, this method will fail. So that is actually motivation for the upcoming new methods in the literature. But this method actually has given a new direction to the literature, like where you can use adaptive signal processing techniques, or just based on the data, like data processing, without designing basis functions. So it is one kind of actually, this is one kind of decomposition like onion. If you see the complete onion, then it has different layers. So it is removing different layers from the onion, not salad one. It is complete actual onion. So that's, we are removing different layers from the data. So after that, this actually empirical mode decomposition that has limitations. One of the limitation actually it has mode mixing problem. So like whatever IMFs we get, and theoretically, by whatever like conceptually, according to methodology, it should have one frequency component. But when you see in real like implementation of the EMD method, then it has mode mixing problem. So in one IMF you have two scales. So this is the one of the motivation, and second one, that it doesn't have any mathematical theory. So this is whatever this EMD method has been proposed, it is based on the empirical study. So it is just like a simulation based study, and these results they don't have any mathematical background. So motivated by that, this recently empirical wavelet transform has been proposed. So generally in conventional wavelet transform, what we do, we design basis functions from our side, but this empirical wavelet transform is a little bit different. You don't need to design basis function from your side. You just take the Fourier spectrum, and like maximum minima in time domain that empirical mode decomposition was doing, that same thing we will do in frequency domain. So we take the Fourier spectrum, we determine the maximum minima, and you separate out the components in frequency domain, and then we design wavelet filters to separate out these components. So it is a mixture of two approaches, empirical mode decomposition and wavelet transform. So that is why we call it empirical wavelet transform. So in this actually work, we have proposed this multivariate empirical wavelet transform and its application for epileptic seizure detection from EEG signal. So human brain is very complicated and it is highly nonlinear system. Even if you record like 5 trials of your EEG signal, it will not look same. They actually is very subjective in nature, because it is brain is very difficult to understand. And whatever we understand about the brain, that is very useful to do many tasks. So electroencephalogram, that EEG, actually measures the electrical activity of the brain, and where during this epilepsy, this all neurons in the brain, they synchronize together and they generate very high electrical activity. And due to that, when you see the EEG signal, there is presence of spikes and large amplitude. So these actually, when we go to hospital, neurologist, they see these features to identify the epilepsy from the EEG signals. So in this work, actually, we have proposed a signal processing machine learning based technique to develop automated system or computer-aided medical diagnosis system which can detect epileptic seizures from EEG signal in efficient manner. So epilepsy affects around 2% of the population of the world, and we have actually proposed this empirical wavelet transform based approach for patient-specific epileptic seizure detection using EEG signals. And here you can see this is actually human brain. There's like frontal lobe, parietal lobe, and occipital lobe, temporal. So these 4 lobes are the major lobes, and whatever we do, this actually these activities they are associated with the one of the regions. So this actually brain is the master of the body, and whatever we do in some way, directly or indirectly, it has connection with the brain. So these lobes are very important to understand the this brain's activity. So for that, this international 10 to 20 system electrode can be used, and this is electrodes are so nicely arranged that you can record the EEG signal for different parts of the brain. So here now, instead of taking one signal, now we will take actually this multiple signals together. So this is one example of 2-channel EEG signals, so that you can, they are recorded at a time from the person who has epilepsy. So motivation of empirical wavelet transform already I have explained you, because this empirical mode decomposition and mode mixing problem, and second one doesn't have mathematical background. So this empirical wavelet transform is very simple approach. It has mainly 3 steps. We compute Fourier spectrum, and then in Fourier spectrum we are assuming that these components, they are well localized in frequency domain. So different segments in the frequency domain can be obtained using this boundary detection approach, and then corresponding to these different segments of frequency bands, we design wavelet filters, and by using these filters, we can separate out these intrinsic mode functions present in the signal using this empirical wavelet transform approach. So what we have done in this work, we have extended this empirical wavelet transform over multivariate signals. Then we have proposed time frequency representation of multivariate signals based on this EWT with application to epileptic seizure detection. So now suppose you have this multi-channel data here, you can see, and now each channel, if you apply this empirical wavelet transform, then this is also actually each channel EEG signal is different. So your Fourier spectrum will be different. Then your boundaries will be different, and then number of obtained components will be different. So this is actually a serious problem when you apply this adaptive signal processing techniques for biomedical applications. So what actually we have suggested, you take the Fourier compute the Fourier spectrum of each channel, and then take average of that. So this is the average spectrum or mean spectrum that is computed from the Fourier spectrum of all channels. Then you design wavelet filters based on this Fourier spectrum, the average Fourier spectrum. And then in the whatever wavelets you have designed, that you use for the filtering out the each channel. So in that way, you will have same number of components from the each channel. And then we actually, this is one of the important actually use of the this kind of signal processing techniques. One of the important concept in signal processing that we use, that is analytic signal representation. That was proposed by the David Hilbert. He is from Germany. He was from Germany, and he says like you can compute instantaneous frequency of the signal using Hilbert transform. But in real life signals, they are multi-component signal. So that method was not actually useful for a long time. But after coming this Hilbert-Wang transform, that actually Wang decomposition, empirical mode decomposition, and these methods, they are decomposing this complicated signal in terms of monocomponent. And where nicely you can apply Hilbert transform. So that is why this EMD based time frequency representation is also known as Hilbert-Wang transform. So that actually there is good application of Hilbert transform. So here actually this, once you have this monocomponent signals or IMFs from the each channel, then you can apply Hilbert transform to convert them into analytic signal representation, and then you determine amplitude, envelope, and instantaneous frequency of these IMFs or amplitude and frequency modulated signals. So after getting this amplitude and frequency modulated signals or amplitude, envelope, and instantaneous frequency of each channel for each component, then by using this formula, we determine joint instantaneous frequency and joint instantaneous amplitude. So here actually we include all channels together to determine that a particular mode's amplitude, envelope, and instantaneous frequency. So by using this, we propose multivariate time frequency coefficients in each oscillatory level by using this expression, and this can be generalized for all modes present in the signal. So that is the last expression gives you the time frequency representation for multi-channel signals which has multiple, each channel has multiple components, but by doing this, actually whatever we have proposed average spectrum based filter design, which gives you the same number of components for each channel. So in that way you will have nice time frequency representation of multivariate signal. So like whatever conventional time frequency representation you use in EEG signal processing, such kind of time frequency representation can be used. That will be actually, that is taking care of the all EEG signals, all channels at a time. So this epileptic seizures, they are actually sensitive to the amplitude of the signal. So due to that reason, we have actually proposed features which are actually dependent on joint instantaneous amplitude, or this is also known as joint amplitude in Bilas. So this first one is mean of joint instantaneous amplitude, which is expressed mathematically by this expression, and mean monotonic absolute amplitude modulation change, which is expressed by this mathematical expression. And third one is variance of monotonic amplitude modulation change, which is expressed by this mathematical expression. So these actually these features have been proposed by us, and they are based on the multivariate time frequency representation. So this is actually complete proposed epileptic seizure detection system. So for this study purpose, we have taken this PhysioNet CHB MIT scale PG database, which has recording from 23 epileptic patients, and this actually database has 20 channels EEG signals. Now, if you apply all these 23 channels together, then actually a lot of computational complexity is required. So epileptic seizure detection, we want to have real-time actually processing. It should detection of the epilepsy should be done in real-time manner. So such kind of systems are very useful. Suppose, for example, somebody driving a car and he or she is going to have epilepsy attack. Such methods can detect in advance that you are going to have epilepsy attack, and epilepsy drugs, medicines can be taken and they can be bypassed. So the detection, epileptic seizure detection system should be having low computational complexity, so it can be implemented for real-time diagnosis. So here, instead of using these 23 channels of the data EEG signal, we have proposed channel selection criteria. So which includes first channel selection with least standard deviation, and after that other 4 channels are based on the relatively higher mutual information with the first selected channel. So in that way you have 5 selected channels, and then you apply this multivariate empirical wavelet transform for these 5 channels EEG signals. Then it will give you in all these 5 channels, you will have same number of modes, because you are using average spectrum to design the filter bank using wavelet filters. So you can see the 5 channels, each channel has 10 modes. After that, for each mode, we determine instantaneous amplitude and frequency, and that way, so 5 channels, each mode will have 2, like this instantaneous frequency and amplitude in Miller, and for 10, this 10 modes. So based on the previous explained these formulas, we determine joint instantaneous amplitude and frequency for each mode, and where we are considering all channels in the computation of these parameters. And from that, we extract the features from mode 1, mode 2, and up to mode 10. And then these features actually, when you give to this as an input to machine learning classifier, then we have seen still some feature processing is required. So that we have proposed some feature processing that we will see in this talk. And these processed features are given as an input to machine learning classifier, where nicely on automated manner, the seizure and seizure-free EEG signals can be classified. So this is one very interesting example. Here you can see this multivariate seizure EEG signal, and that one, and this 5 channels, and this is for 5 channels multivariate seizure-free EEG signal. So for these, actually now this time frequency representation is computed using these 5 channels. So this is the time frequency representation obtained using this 5 channel EEG signal seizure case, and this is the time frequency representation computed using this 5 channel seizure-free EEG signal. So this is actually one of very good result, and that is very useful for computer-aided medical diagnosis and also for telemedicine. So like in rural areas, we have shortage of doctors, and sometimes there is no doctor. So this actually, these methods, when you implement in the form of computers, software, they can be nicely integrated with the computers, laptop, smartphones, and a smartphone will become really smart. And nicely it can detect epilepsy using such kind of signature. Just you take EEG signal and you extract these features, give to the, determine this plot, and based on the plot, you can say that whether you have seizure or not. So this is very useful for automated identification of the seizures. And also such kind of methods are very useful for the neurologists because doctors are less and patients are many. So these actually help, these methods in the form of software, they can help doctors to perform the diagnosis in efficient manner. So here you can see. Yeah.
I think I have a stupid question.
No. Yeah, good question. Please.
I think you are doing something different from what everybody is doing. Because nowadays people just have a deep learning box, and people just use deep learning, just one box.
Yeah, that is so. Yeah. That is actually deep learning is also fine here. The signal processing is there are two important parts of the biomedical data. One is analysis, and second one is classification. Analysis can help you to get good interpretation. This deep learning classifies like black box. It will separate two classes. It is seizure free. But what is the severity of the disease? What is the level of the disease that can be correlated with the nice features? So this feature actually has own importance. Like if you have good features, that can be associated with the disease, and the level of the disease can be determined based on the features. That is what we do in medical. We go, no, this is the value of this is the range. So this feature range, your parameter is coming in this range, then this is the decision can be taken in that way. So both are having their own applications.
I have a question to the slide before this one. I was wondering where the multivariate data really comes in, right? Because, okay, you have multivariate data coming in, but then you find the different modes on the average signal.
No, this average, yeah, because this is from the average spectrum.
Okay, the average spectrum.
But spectrum is just like boundaries. Then from the boundaries, we are obtaining components from the signal itself.
Okay, I see.
Okay. So whatever this basis, whatever components are coming, they are part of each channel.
Okay, thanks. Yeah.
So for each channel, we are using the same filter range.
Okay, same filter run all the channels.
Yeah. So in that way, you will have mode alignment property. Otherwise, you will have different components for each channel, and it is problematic how to compare each other, because you should have same numbers. Then only you are comparable. So here you can see this during epilepsy, this all neurons they synchronize together and they generate very high electrical activity to show that there is a presence of spikes in the data. So here you can see this spike actually represents all frequency component in the frequency domain. So in this time frequency plan also you can see when a person has epilepsy, there is a presence of high frequency component as well as low frequency components. But this is not the case when there is a seizure free. In this case, only low frequency components are present. So this is actually nice signature from the physiological point of view also. That is validating our whatever results we get. That is the validation of the what doctors believe. So this can be used as an alternate of the like doctors for the diagnosis of the epilepsy. So after that, once you have these features for this all modes, that you can see this mean of joint stiffness amplitude for all 10 modes, and mean monotonic absolute amplitude modulation this change, and variance of monotonic amplitude modulation change. For this all actually 10 modes, this is not showing good discrimination between seizure and seizure-free intervals, and that actually so we have proposed the feature processing. So this moving average filtering for all these features, then you can see the filtered features, and they are showing the good discrimination between seizure and seizure-free intervals. So in the middle we have seizure episode, and that is not clear from this without feature processing. So once you perform the feature processing, then nicely there is a improvement, the discrimination between seizure and seizure-free intervals. That is more visible. It also can be improved when you multiply all of them together. So we have proposed this moving average filtering of these features, and after that Hadamard product, and then you have joint feature vectors for each features from the 10 modes. So you see here, so this is the epileptic seizure and surface EEG signal that is actually it has noise, and it is not easy where epileptic seizure is there episode. But when you see the joint features, there is nice presence of the seizure can be detected. So this is the strength of the feature that deep learning cannot do. These features, and nicely you can see the localization of the feature, that in the this is the actually here epileptic seizure is there, but it is not clear from the raw signal. But when you perform this good signal processing technique, then nicely you can detect the features.
Yeah, but
it can tell you that this place, this epileptic episode is there.
But in some sense, you did something like deep learning. You have a matrix layer. The difference, only difference is that like in deep learning, everything is learned.
It is more general. It will take time. This here we are using some parts. So selection of the spoon depends on the type of food. If you want your noodles, then you use fork, because your food is discontinuous and spoon is also discontinuous. So if you want to analyze this complicated data, we need complicated signal processing technology. So that is whatever actually the signal processing technique required that we are using. So like we don't use one spoon for handling all foods. So we go to restaurant and depends on the food we select the spoon. Similarly, here these features are very playing important role, and nicely you can detect even the localization you can see of this epileptic seizure is very good. It is not easy without signal processing.
I know. I agree with you. I'm just thinking, because I don't work on epilepsy, I'm thinking how can I move it to other.
This Bonn University in Germany, this is one of the, even EEG signal was invented in Germany by the Berger. It was invented in Germany, Berger, but it's known as alpha waves called Berger waves. And this Bonn University, their database is the benchmark database for epilepsy. They detect epilepsy based on the intracranial EEG signal they record from the inside, because sometimes it is difficult to detect the seizures. But this method can detect seizures in the presence of noise, because surface EEG signal when record from outside, there is a effect of noise. So, but this method is also able to handle this noise effect also. Yes. And then actually we have given this these features as input to machine learning classifier, like random forest classifier, and it has given for this complete database 99.57% specificity, 97.91% sensitivity, and 99.41% accuracy. And there is a lot of actually study has been done, and this is actually one of the challenging database. There is very good groups entire world, they work on this database, and we have compared, and that our method has provided best among other methods compared to other methods. They have been studied on the same database. After that, this empirical mode decomposition that we have seen, that this empirical wavelet transform was the one of the solution for overcoming the limitations of the Emt method. And recently, the iterative filtering, this is another approach has come up to handle this actually limitations of the Emt method. So here actually, this is also very interesting approach. Here design of the filter depends on the maximum minimum, extremas. So like here, what we are doing in empirical wavelet transform using wavelet filters, here these filters will work based on the maximum minimum of the signal in time. So this filter cutoff frequency or this moving average filter will be designed based on the maximum minimum present in the signal. So here, this is actually formula for the length of this filter, that L equals to alpha capital N upon K. So N is the sample size of the data, and K is the number of extremas. So number of extremas, if higher, like the high frequency component, then your filter length will be less. And for filter length less, this cutoff frequency proportional to 1 upon the filter length. So this cutoff frequency of that filter will be higher. So when you have high frequency component present in the signal, then relatively your cutoff frequency will be higher. once you high frequency component in the form of IMF you remove from the data using this iterative approach, then next high frequency component will become the highest frequency. So in that way, actually, we repeat this filtering process for this different iterations, and we get the all possible IMFs from the signal. So just I will demonstrate it with the example. So this is actually residual, and X is the signal, and this LX is the low pass filtered signal based on that cutoff frequency. So this residual that is actually will satisfy these conditions of the IMF, and then we call it IMF. So here you can see this is for like this signal has three components in frequency domain. So this means it has three intrinsic mode functions, and now we have designed this filter which will cover first two frequency bands. So when you subtract this spectrum of the this filtered signal with the spectrum of the signal, then you will have the spectrum of the first IMF. So now in the next iteration, this first IMF spectrum will be subtracted from the signal. So now these three frequency bands are there. This highest frequency band will be removed. So second iteration, you will have first two bands. So now the second IMF will become the highest IMF here. So next step, now next trial, this is a filter, design filter. And from the filtered, this is the filtered out component. When you subtract this filtered out component from the signal spectrum, then you will have this second IMF. Now first and second IMF, both will be subtracted from the signal. Then in the end, you have third IMF. So in that way, this the spectrum, the IMF, the highest frequency component is actually removed with the help of filter in different steps. So here you have seen this method, actually iterative filtering based approach. This is also actually when you apply this multi-channel data. So each signal will have different spectrum. So number of components will be different for each channel of the multi-channel data. So for that, actually, we have proposed this improvement in this iterative filtering that we call multivariate iterative filtering. So here you can see now this is the flow chart for iterative filtering for a univariate case when you have one channel data. And this right hand side, you see the flow chart of the proposed approach for multi-channel data. So here is simple, like you have signal, then we determine extremas, and then based on this extremas, we design this filter and length, and from the length we determine this cutoff frequency, and that is actually focal Planck equation. That is a very nice structure. This is used for the designing this filter, because in that there is no, like when you have a rectangular like same weightage for this filter, then in the frequency domain it will have spectral leakages. So in order to avoid such kind of situation, this Fokker and Planck equation has been used in this for designing this filter. So this based on this cutoff the filter length, cutoff frequency design, and then we have filter, and this filtered signal is subtracted from the signal. Then you have residual. Then there are two stopping criteria. So first stopping criteria checks that the standard deviation with the previous iteration is if it is around 0.001, then we will stop it. So we say this is the first IMF. And then we check second criteria, this number of extremas should be less than 3. So it is like sine cosine form. And if these conditions are not satisfied, then we stop this process. So in that way, we take the signal, we determine maximum minima, extremas, then we design the filters, then subtract the filtered signal from the signal, then residual should satisfy the IMF conditions. If it is not satisfied, then we repeat the same process, different iterations. And once this is satisfied, then we call it as first IMF. Then after, for the next process, we subtract this first IMF from the signal and repeat the same process. So in that way, all possible IMFs are obtained. And same now we have actually extended this for multivariate case when you have multi-channel data. So you have multi-channel signals, then determine the extrema for each channel. Now, if you do channel-wise processing, then again same problem will come, because each channel has different maximum minima or extremas. So we determine, we take the maximum extremas from all of the channels, and based on that, actually we design this filter length, and from this filter length we determine the cutoff frequency, and we design the filter which we will use for all single channels, all channels separately. In that way, you will have same number of components from each channel, and this actually we will explain this with the help of one diagram. So this is a step-by-step illustration as is shown by this diagram of this multivariate iterative filtering. So here you can see this signal, two channels are there, and first channel has two frequency components, and the second channel has one frequency component. So if you apply iterative filtering to each channel, then first case you will have two IMFs, in second case you will have one IMF. But now what we have done, you select the channel. So this is the first design channel for design filter for the first channel, and this is the design this filter for the second channel. So you select the highest cutoff frequency or maxima of the minimas of extremas for both channels. So this higher cutoff frequency, so this filter will be selected out of these two channels, and that will be used for the both of them to filter out. And after that, these filtered signals from this common filter will be subtracted from this two channel EEG signal, channel wise. So in that way, this is the now first IMF, but this IMF will not be one component. It will have it is one kind of vector. So this is first IMF, but two channel first IMF. Now you subtract this first IMF from the signal, two channel signal. Then in next actually iteration, you will have the first IMF. This is the actually residual, where first channel has one IMF and second channel has one IMF. Now you design the filters here. So these are design filter for this first channel, and this is a design filter for second channel, and take the maximum of both. So maximum will be this one. So this will be used for both the channels to filter out, and then filtered signal will be subtracted from the this residual. So this is the second IMF. So here is the two channel second IMF. Now first IMF, second IMF, both will be subtracted from the signal. So this is the residual for the third iteration or third IMF. And here now you design the filter. So this in both cases filter is centered around 0. So this is the maximum. The filter is same for both cases. So this is the same filter will be used. So there is no filtering. So this means your this process has become stable. Now no iterations are required, and you got third IMF. So in that way, this two channel data, two channel EEG signal, for example, have been represented by two channel first IMF, two channel second IMF, and two channel third IMF. It's very actually interesting approach. This most of the whatever we see cognitive, all these applications, medical, epilepsy, emotions, we always consider brain is important part. But when you see actually in real life, this whatever we do, most of the actually is different parts are playing role. We are studying emotions, so it is based on the EEG signal, but electrocardiogram signal is also actually playing role in the emotion study. So now we are combining electrocardiogram signal, phonocardiogram signal, electroencephalogram, different biomedical signals for human emotion detection. So here actually now when you have multimodal signals, when you have different kind of biomedical signals, how you do analysis. So this actually this multivariate signal processing that we have proposed, it is very useful tool for studying such kind of signals together. So one of the application that in ICU, where we have this ECG signal from lead 1, ECG signal from lead 2, and third one is this respiratory signal, and fourth one is seismocardiogram signal. So they actually, when you go to ICU, you will find that there are multimodal signals. There are many signals they are recording at a time, because we want to have more reliable decision, reliable diagnosis. So instead of taking decision from the one signal, we use multiple signals at a time. So when you use these 4 signals, they are different in nature, but they have a lot of actually correlated information. In India, there are actually old doctors, we used to call them Vedas. So they based on the wrist, they hold here and they will tell you whether you are happy or not, you had food or not. So these signals actually they can sense it. So yeah, in China also this, so wrist, based on the wrist, they will not ask you anything, but based on this kind of signal, they do lot of actually diagnosis. They will tell you you did not have food today, but this signal has lot of information. So whatever ECG is giving, these wrist signals, EEG signals, they all are having correlated information. So this multimodal now, how this analysis, so whatever we have proposed, this multi-channel signal processing. So we have combined this for all actually signals as a multi-channel, and then you can see for this ECG1, ECG2, lead 1, lead 2 ECG signals, and breathing, seismocardiogram, and this respiratory. In all cases, you can have same actually components. For example, like 11th IMF, they represent same frequency component. So for example, if you are interested in heart rate, you can actually obtain this from the various models, various signals at a time. If you are interested in emotions, so this method actually, these multiple models can give you correlated information for emotions in the fixed frequency band, but they are based on the all multiple channels. So like 11th, 12th IMF, they actually represent the same frequency information. So this mode alignment property is there. After that, actually, this approach we have studied for schizophrenia detection using EEG signal based on the multivariate iterative filtering. So schizophrenia is a chronic and severe mental illness, and around in the entire world, around 20 million people actually they suffer from this disease, and more than 1 million people in India. So it has symptoms like hallucinations, fixed false belief, hallucinations, experience of seeing, hearing, tasting, smelling, or feeling that does not really occur, and disorganized speech and thinking, abnormal motor behavior. So for that, actually, this is a proposed approach and for schizophrenia detection. So we have M channels at a time. Then we have performed segmentation of 25 seconds. Then we apply some pre-processing. Then iterative filtering for multi-channel EEG signals. So this is like multivariate iterative filtering. Then we have for all M channels, we have N number of modes. They are same for all these channels. Then actually we have proposed this rhythms for multi-channel data. That is actually one kind of different work that you will see in the literature. So now instead of rhythms, like whatever you do from the EEG signal, you take channel wise, then determine the rhythms. Here you will have for each channel, you will have separate rhythms. So multiple EEG signals, you have multiple EEG rhythms based on this approach. And then once you have rhythms, then you extract features from EEG rhythms. Then we perform classification, which will give you this automated identification of schizophrenia from the EEG signals. So for this study purpose, this publicly available data set for schizophrenia from Institute of Psychiatry and Neurology, this Warsaw, Poland, has been used in this study. And it has 14 patients. They are from schizophrenia, and they include 7 males and 7 females. For healthy EEG signals have been recorded from 14 healthy people, and they have 7 males and 7 females. And these signals have been recorded from 19 channels, and sampling rate is 250 Hz, and this entire recording duration is around 15 minutes. So here actually is a very interesting result you see. So now you have 3 channels, FZ, CZ, PZ, their EEG signals. Now you see the second IMF, third IMF, fourth IMF. They are obtained using multivariate iterative filtering, and they represent the same frequency components. In the time domain you can see, and it is clear from the power spectral density of these 3 components, you have mode alignment property. So each channel, whatever component is giving, they are actually well aligned with each other in the frequency domain. So you can have unique information and at the same time correlated information that can be compared. Different classes can be compared in a nice manner. Now, in order to separate the rhythms for using this multivariate filtering, we have proposed use of mean frequency. So what we do actually for the each channel, you have a different number of components, and from the components we determine the mean frequency. If these mean frequencies, for example, is between 0.1 Hertz to 4 Hertz, then we separate it and we assume this is part of, for example, a rhythm. Then for other next any IMF mean frequency belongs to this range, then we take such all IMFs and we will combine all of them to make this delta rhythm. Similarly, we will do for theta rhythm, alpha rhythm, beta rhythm, gamma rhythm for all channels. So in that way, if you see here, these are the separated rhythm: delta, theta, alpha, beta, gamma for multi-channel. So for example, now here 3 channels are there. So now you have 3 channels of the rhythms. For each channel, you have separate rhythms. So you can do a lot of processing. You can determine the various features you have rhythms in time domain, frequency domain. You can go for time frequency domain also from the rhythms. So after that, we have extracted these parameters, Azeroth activity, Azeroth mobility, and Azeroth complexity. Whose mathematical expressions can be seen in this table. And then for a trial, this total features, that is actually, we have 19 channels. So for each channel, we have 5 rhythms, and we have 3 Azeroth parameters. So total 285 features comes out. That is actually, if you use all of the features, then this method will require a lot of computational complexity. So in order to that, actually, we have proposed this student t-test and this course-wise statistical test to select the significant features out of the total features. So based on that probability value, if probability value is less than 0.05, then we call it statistically significant difference between the two classes. And here, based on the probability value, we have selected best 30 features for out of 285 features. And then this you can see the most 10 features. This is this box plots obtained using this Kruskal-Weiss statistical test. And from this plot, you can see these features are actually discriminative in nature. They are showing the difference between the schizophrenia and healthy classes of EEG signals. After that, this selection of the 30 features actually done based on the trial and error method. So you can see from this plot, when you go for 30 features, then it is giving you best classification accuracy, and after that is not increasing. So based on trial and error, the 98.9% classification accuracy that is obtained using 30 features. So we have studied this support vector machine with cubic, quadrature, linear kernels, linear discriminant, k nearest neighborhood, recently classifiers. And then in order to measure the performance of the proposed approach, this performance measures accuracy, sensitivity, specificity, and positive predictive value. And this table shows the this performance measures for different classifiers with 30 features. 5-fold cross validation, 10-fold cross validation. So 10-fold cross validation means like entire features we divide to 10 parts, and 9 parts we use for the training purpose, the remaining one for the testing purpose, and we repeat this for different 10 other combinations, and then we take average of all of them. So that is 10-fold. The same thing we do for 5-fold cross validation, and here this you can see accuracy, sensitivity, specificity, positive predictive value, and area under ROC curve. That is also one of the important actually parameter. That is, and if area under ROC curve is approaching 1, this means it is good classified. So here you can see this 10-fold cross validation with a support vector machine with cubic kernel function. Actually, it gives you better performance. And then actually we have compared this proposed method with other existing methods in the literature, which have been studied in the same database. And our proposed method actually has provided better performance than other existing approaches. So this is the conclusion of this talk. The proposed multivariate empirical wavelet transform and multivariate filtering are able to decompose this multi-channel and multivariate signal into meaningful components. And mode alignment is the most important properties of the multivariate decomposition approaches, and proposed methods properly align the similar oscillatory components across the different channels. And the proposed methods have provided good detection performance for epilepsy and schizophrenia diagnosis based on the scale PG signals. And the proposed automated systems can be useful for assisting neurologists in their decision-making process. And the computer smartphone with the proposed algorithms can be used for the diagnosis of these neurological disorders in rural areas where we have shortage of doctors. So this actually work is based on this recently published some of our work based on these publications. And please go through these papers in order to have more detailed information about the presented work. Yeah. Thank you very much. If you have any questions, please.